Hello everyone, my name is Dhruv Kumar Kaushal. Today I am going to be presenting the paper titled Efficient Estimation of Word Representation in Vector Space. Quickly, if we walk through what we will cover today, we will start with the motivation like why do we need a special way to represent words. Then I will give you some background on how words were handled before this paper. After that, we will dive into core idea of word2vec and its two model architecture. We will also look into some math and training details like how the model actually learns the evaluation approach and the results from the paper. And finally, we will see the most famous result, which is a vector arithmetic, where you can literally do king minus man plus woman and get queen. I will be also using real examples, worked out maths, and some code output. So hopefully it says concrete and easy to follow. So coming to the first part, motivation, where the question we can see is how does a computer currently understand words? So the traditional approach was to treat each word as completely independent symbol. You assign every word in your vocabulary a unique number, like apple gets index 1, mango gets index 2, dog gets 3, cat gets 4, and so on. Now here is the fundamental problem with this. If I ask the computer, is apple more similar to mango or more similar to dog? The model has absolutely no idea, because the model apple is just the number 1, mango is 2, dog is 3. They are all equally far apart. There is no relationship encoded anywhere. This is a huge limitation. Think about it. If a model has learned something about the word dog, shouldn't the knowledge transfer at least a little bit to the word cat? They are both animals, both pets. They appear in similar sentences, but with the index based representation, there is no data knowledge transfer. So the central question this paper asks is, can we represent words as numbers such that similar words end up having similar representation? And the answer is yes from the paper, and that's exactly how word2vec does. Let me make this more concrete with real world example. Suppose your NLP system has been trained on corpus and has seen this sentence: I had delicious mango yesterday. Now during testing it sees an incomplete sentence: I had a delicious yesterday. If the model knows that mango, papaya, and banana are all fruits that they appear in similar contexts, it can make an educated guess. So it knows that the blank should be filled with something edible, something fruit like. But if words are just indices, the model sees mango as number 47, papaya as number 3112, 312. It has no way to know they are related. It cannot generalize. Looking into another example, if the model has seen a sentence like he went to Paris for vacation, and now it sees she went to dash for vacation. Ideally, it should predict a city: Paris, London, Tokyo, something like that. For this to work, the model needs to know that Paris, London, and Tokyo are all of same type of word. They are cities and they belong to the same context. This idea actually has a name in linguistics. It is called the distributional hypothesis. Uh, you shall know a word by the company it keeps, which means that words that appear in similar contexts have similar meanings. Word2vec operations exactly this idea. So coming to the background, before word2vec, the standard way to feed words into neural network was using one hot vector. It works in this way, like say your vocabulary has 5 words: king, queen, man, woman, apple. King becomes 1 0 0 0 0. Queen becomes 0 comma 1 comma 0 comma 0 comma 0. Man becomes 0 comma 0 1 comma 0 comma 0, and so on. Each word gets a vector of length equal to the vocabulary size with exactly 1 and all zeros everywhere else. Now what are the problem with this? First, the vectors are huge. If your vocabulary has 1 million words, every word is a vector of 1 million dimension. That's extremely memory inefficient. Secondly, one and more importantly, all words are equally dissimilar to each other. The dot product of king and queen is 0. The dot product of king and apple is also 0. They are all orthogonal to each other. There is no mathematical relationship between any two words. Thirdly, there is no generalization. If the model learns something about king, it learns nothing about queen. The representations are completely independent. What we actually want is dense, low dimensional vectors, maybe 300 numbers for each word, where the values themselves encode meaning. So king and queen are close together and apple is far away from both. That's the goal, and that's what word2vec gives us. So before we get to word2vec, let me give you a brief history of how language modeling was done before this paper. The most classic approach was n-gram language models. The idea is simple. The uh, predict the next word based on the previous n minus 1 words using frequency counts from a large corpus. For a bigram model, n equals 2. You estimate the probability of cat given the equals the count of the cat divided by the count of the. For a trigram n equals 3. You condition on two previous words. But here are some problems with this. Firstly, sparsity. Suppose your sentence contains the phrase the fluffy orange cat. If this exact sequence never appeared in training, its probability is 0. The model completely fails. Secondly, no generalization. The dog barked and the cat meowed are treated as completely unrelated sequences. The model has no idea that dogs and cats are both animals. Thirdly, memory. As n increases, the number of possible n-grams explodes. Storing all trigrams or 4 grams from similar trillion word corpus is impractical. And crucially, no semantic understanding. The model is just counting patterns, it doesn't understand the Paris is the city or the king and queen are related. Neural network language models came next and did much better, but they came with their own problems, which will I explain now. So neural networks language models or NNLMs were a big improvement. The architecture was proposed in 2003 works like this. You take previous n words as input, each word is represented as a one hot vector and fed into projection layer, which maps each word to a dense vector of dimension d. So the projection layer has size n times d. Then there is non-linear hidden layer of size h, typically 500 to 1000 units, and then an output softmax layer over the entire vocabulary V. Now let's look at the computational complexity per training example. So Q is equal to n into d plus n into d into h plus h into v. So the dominating term here is h times v. If h is 1000 and v is 1 million, that's already 1 billion operations just for output layer. And this happens for every single training word. With a corpus of billion words, training this takes weeks. The key inside the word2vec paper makes is the bottleneck comes from the non-linear hidden layer. What if we just removed it? Would we lose too much accuracy or would we compensate by training on way more data? The answer is surprisingly the second option. So there was also another model that was popular at that time, which is RNN model, which RNN LM model proposed by the same lead in 2010. This key innovation here was the use of recurrent hidden state. At each time step t, the hidden state ht is computed as ht is equal to sigma of whx times xt plus wh times ht minus 1. What this means is the hidden state at time t depends on the current word xt and the previous hidden state ht minus 1. This creates a hidden memory and the model can theoretically remember things that happened many steps ago. The output is then yt is equal to softmax of wh times ht. The computational complexity is q is equal to h into h plus h into v. Advantages of over NLM is way more and no need to specify fixed context window. The recurrent state handles that. Theoretically captures longer dependencies. But the problem remains. The h times v term still dominates. The h times h matrix multiplication is also expensive. In the paper, RNNLM took 8 weeks to train on a single CPU. So the powerful models we have, but they are too slow. So the word2vec paper asked, can we strip away the expensive parts and still get excellent representation? So now coming to the core insight of word2vec, this is a main idea of how word2vec is innovated. So word2vec's key innovation is beautifully simple. Remove the non-linear hidden layer entirely. On the left, the old neural LM input to projection to hidden layer to output. The hidden layer gives a model a lot of expressive power, but it's a computational bottleneck. On the right, word2vec gives input to projection to directly output. That's it, no hidden layer. Now you might think won't be removing the hidden layer make the model much worse? And yes, the model is less expressive. It can learn as complex patterns per training example. But here is the key trade-off the author makes, and it's a philosophical argument that I think is really profound. Simple models trained on huge data outperform complex models trained on less data. By removing the hidden layer, each training step becomes so cheap that you can train on vastly more data in that same time. Here is a real world analogy. Imagine you want to get good at a language. Option 1, you take a small intensive course with a brilliant expert tutor. Option 2, you just immerse yourself and read 10,000 books. Often breadth of exposure beats depth of instruction. The brain, or in this case the model, figures out the pattern and on its own if you give it enough examples. The result, word2vec trains on 1.6 billion words in less than a day. The RNLM took 8 weeks on similar data, and despite being simpler, word2vec's word vectors are dramatically better. That's the inside, simplicity plus scale wins. So coming to the architecture part, word2vec actually proposes two architecture. Let me introduce both before going deep into either. The first is continuous bag of words. Look at the left side of the diagram. You have surrounding context word as input. WT minus 2, WT minus 1, WT plus 1, WT plus 2. They all get summed up in a projection layer and the model tries to predict the central word WT. Think of it as fill in the blank task. The cat dash on the mat. Given the surrounding words, predict sat. The second is skipgram. Look at the right side. Here it is reversed. You take the center word WT as input and the model tries to predict surrounding context words. Same sentence, the cat sat on the mat, but now given sat, predict the cat on the. Two different learning objectives but the same goal. By forcing the model to predict context from word, the model is forced to learn what kind of word each word is, and that information gets encoded in the vector. At a high level, continuous bag of word is faster and works better for frequent words and syntactic tasks. Skipgram is slower but much better at semantic tasks and rare words. We'll see in both in detail now. So coming to the continuous bag of words deep diving, take this sentence. The cat sat on the mat. Let's say our target word is sat. That's what we want to predict. And our context window size C is 2. So we to look towards left and towards right. Our context is the cat on the. So coming to the steps, the first step is we look up the embedding vector for each context word. We get v the cat, v cat, v on, v the. These are rows from our embedding matrix W. Each is a d-dimensional vector. Step 2 is we average these four vectors. We average the 1/4 times the cat on the. Step 3, we multiply the average vector by the output weight matrix W prime. We apply on the fourth step, we apply softmax to get a probability distribution over the entire vocabulary. Step 5 is we train by maximizing the probability of the correct word, which is sat. Now, why is it called a bag of words? Because we average the context words. The order doesn't matter. The cat on the, and cat the on produce the same average vector. We throw them in a bag, mix them up, and take the average. The training complexity is Q is equal to n into d plus d into log 2v. Notice no h term, no hidden layer multiplication, and we use log 2v instead of v, thanks to hierarchical softmax, which we will explain in next few slides. This is dramatically cheaper than NNLM or RNNLM. So coming to the skipgram part, we take the same sentence as example. The cat sat on the mat, same target word sat, same size, same window size, c equals 2. Now sat is the input and we want to predict the cat on the. So coming to the steps, step 1, we look up the embedding of the input word v sat. For each context position, multiply vector sat by the output matrix W prime. Then apply softmax and compute the probability of the context word. Step 3 is training single. The training single is to maximize the probability of each correct context word given sat as input. And here is a subtle detail. The window size is actually randomly sampled during training. We pick R uniformly from 1 to C and use R words from before and R from after. This means closer words are sampled more often, which makes sense because closer words are usually more relevant. But why does this skipgram learn such good semantic representation? Think about it. If sat and rested both appear in similar sentence, the cat sat on the mat and the cat rested on the mat, then when training skipgram, both words will be trained to predict the cat on the as context words. So over many training examples, their vectors get pulled toward the same region in space. They end up close together because they mean similar things. Training complexity is here is Q is equal to C into bracket D plus D into log word2v. It is slightly more expensive than bag of words because we make multiple prediction per word, but the richer prediction lead to much better semantic understanding. Coming to the embedding matrix, let me now clarify what the model is actually learning. When we train word2vec, we have two matrices. W, which is the input embedding matrix of size V by D, W prime, the output matrix, also V by D. Uh, each row of W is the vector for one word. After training, we keep W and throw away W prime. The rows of W, that's our word vector. That's the whole point. Let me show you a tiny concrete example. Suppose vocabulary king, queen, man, woman and d is equal to 3 dimensions. Before training, these are just random numbers. After training on large corpus, the model might learn vectors like king, which has a matrix, queen has a matrix, man has a matrix, and woman has also a matrix. Look at this. King and queen have very similar values in dimension 1 and 2. Man and woman have similar values in dimension 1 and 2. But dimension 3, it's low for king and man, high for queen and woman. Dimension 3 seems to encode gender. And this is remarkable. The model never saw the concept of gender. It was never told that the king and queen differ by gender. It just figured out by training to predict which words appear near which other words. So no human labels, no manually defined features, pure self-supervised learning from the raw test. Now coming to the training objective, let's now formalize the training objective mathematically. For skipgram, we want to maximize the following log likelihood. So L is equal to 1 by t times the sum over all positions t, and for each position. The sum over context offsets j from minus c to plus c, excluding 0, of log p wt plus j, a probability wt plus j wt. Breaking this down, t is the total number of words in the corpus, c is the context window size, wt is the central word, wt plus j is the context word. We are essentially saying for every word in the corpus, maximize the probability of all words around it. The probability itself is defined using softmax, which you can see, and the numerator here is how compatible is the output word wo with the input w1. Denominator normalizes over all words in the vocabulary to make it a valid probability. Here is the problem with it. The denominator sums over all v words. That could be 1 million words. We have to compute this at every single training step. For a billion word corpus, this is completely impractical. So the solution here is hierarchical softmax, which I will cover in next. It reduces v operations down to log 2v operations. So coming to the hierarchical softmax. Hierarchical softmax is a clever trick to make the output computation efficient. The idea is to represent the entire vocabulary as a binary tree. Every word in the tree is a leaf node of this tree. To compute the probability of a word instead of comparing against all v words, you follow the path from root to the leaf for that word. At each internal node, you make a binary decision: go left or go right. The probability of word is the product of probabilities along its path. So the if the path to cat is root, so it goes from root right, left, right, then probability of cat is equal to probability right at root into probability left at node 2 into probability right at node 5. Now here is the smart part. They use Huffman tree. In a Huffman tree, frequent words get shorter codes. They are closer to the root. Rare words get longer codes. They are deeper in the tree. So the words like the, a, of, which appear millions of times might be at depth 3, and rare technical words might be at depth 20. The average path length ends up approximately being log 2 of the unigram perplexity of v. For a vocabulary of 1 million words, this is around 20 steps instead of 1 million. That's 50,000x speed up for output computation, and the paper reports about 2x speed up over even a balanced binary tree, because the Huffman coding takes advantage of the skewed word frequency distribution. This is one of the key engineering innovations that makes word2vec practical.
So hello everyone, I am Saurav. So I'll continue from the next slide. So here another clever trick from the paper was like upsampling frequent words. Think about the word it appears in almost every sentence, and if we train on all occurrence of the, we are doing an enormous number of updates for a word that doesn't really tell us much. Knowing that the appears near king doesn't tell us how much about the king, because the appears near everything. So the solution is, during training, discard each word with a certain probability. And so like if you see the formula, so we have there's a probability of discard of wi is equal to 1 minus square root of t divided by wi, where fwi is the frequency of the word wi and t is the threshold parameter. Typically is like 10 to the power minus point minus 5 or something. Let me compute a real example. Take the it appears with a frequency roughly like 0.05 or like 5% of the all words, and this is the probability calculation. So nearly every occurrence of the is just thrown away during the training. Now take neural. Frequency roughly like 0.0001 or like 0.1% of the words, and this is the probability, and so like it's equivalent to like 68.4%. So the benefit is that first it speeds up the training because we simply process fewer words, and secondly the model gets more updates for a rare informative words. Third, it actually improves the quality of word vectors for the rare words. It's like a win-win situation. Simple idea, big impact. So the next is like we'll move on to the evaluation methodology discussed in this paper. So now let's talk about this. And the author designed a comprehensive test set called a semantic syntactic word relationships test set, and the task is the word analogies. So if you see the example, the format is the Athens is to Greece as a Oslo is to dash. So the answer will be like we compute x equal to vector Oslo minus vector Athens plus vector Greece. Then we find the word in the vocabulary whose vector is closest to x. The correct answer would be like Norway. So this test set has two categories. First is a semantic question which has like 8,816 in total, and which has like capital cities Athens, Greece, and Oslo, Norway, and concurrence like Anglo, Kwanzaa and to Iran, real. City and state like Chicago to Illinois, and the Stockton to California. Man-woman relationship like brother sister and grandson and granddaughter. Similarly, next is the syntactic question. So it has a like 10,600 approx total. So adjective to the verb like apparent to apparently, rapid to rapidly, for the opposites like possibly to impossible, ethical to unethical, similarly, and goes on. So the scoring rule is strict. The answer is correct only if the exact word is the nearest neighbor. Synonym count as a like a wrong. This means 100% accuracy is likely impossible. Word like Oslo might have a like a version as its nearest neighbor in the some model, which is also a Norway city. So, but it is counted as a like a wrong. The author acknowledges this but argue the metric like still correlates well with the practical usefulness. Next will come to a like a formulation of a cosine similarity. So I want to take a moment to explain this part, and because it's a mathematical backbone of how we find the nearest neighbor in the word vectors. So the formula is the cosine similarity between vector a and b. So cosine of a and b is like a dot b divided by the magnitude of a times magnitude of b, which expand is like in this way. For each dimension is divided by the square root of sum of ai squared and times the square root of sum of bi squared. So we'll have a like a basic can have an example. Let's say like v vector of the king is like 0.9 comma 0.3 and vector of queen is like 0.85 and comma 0.35. So an apple we have a 0.1 and 0.95. So like here is the formulation. So we'll get like 0.41, which is not very similar. The interpretation is like 1 means the vector points in exactly the same direction, which means the same meaning. 0 means they are like a perpendicular, so completely unrelated. And -1 means opposite direction. So and why cosine over Euclidean distance? Because cosine ignores the magnitude of the vectors. Magnitude roughly correspond to how frequently a word appears. We don't want frequent words to dominate just because their vectors are large. Cosine focus purely on the direction, so the type of word. So next we'll move on to next slide. We'll discuss the results and time. Now let's look at the actual result from the paper. The first experiment asks how does accuracy change as we vary the number of training words and the number of dimensions. So this table 2 from the paper rows are vector dimensions like 500, 300, 600, and columns are the training data size from 24 million to like 780 approx million words, and numbers are accuracy percentage on the word analogy task. Let's read it. At 50 dimensions, 24 million words, we get 13%, and at 600 dimension and 780 words, we get around 50.4%. Clearly, both more data and more dimension helps. So, but here is the interesting observation: diminishing returns. Going from like 50 to 100 dimensions is a big jump, and going from a 300 100 to 300 is a like still good jump. But the improvement from 300 to 600 is smaller, and same for the data. Doubling data helps, but benefits shrinks. And importantly, you need to scale both together. And a 600 dimensional model trained on only like 24 million words, which is like 24% accuracy, and a 300 dimensional model trained on a 783 words, which is like 45.9% accuracy. And more data beats like more dimension, and when you can't afford both. So the paper derives this equation for that doubling the data has a roughly the same computational cost as a doubling the dimension. So they are interchangeably from a compute budget perspective, but like if you to have a tune based on your specific constraints. So moving to the next slide, where we will next is the like comparing architectures. Now let's compare different model architectures head to head. This is the table 3 from the paper, and all models are trained with like 640 dimensional vectors on the same data set. The columns are like semantic accuracy, syntactic accuracy, and MSR test data. Starting from the bottom, like RNN LM, which is a 9% semantic, 36% syntactic, and the uh, pretty weak. And NNLM has 23% semantic and 53% syntactic, which is like a kind of better. And continuous bag of word is like 24% semantic, 64% syntactic, and better still on like syntax. Skip gram is like 55% semantic, 59% syntactic, and which is like a massive jump on semantics. So like this is like striking, as like skip gram gets 55% on semantic tasks, and that's more than the double NNLMs, which is like 23%, and more than like 6 times the RNNLMs, which is like 9%. And why does skip grams excel at semantic tasks? Thinking about like training objective, in skip grams gives the word Paris, you predict France city, or Aleph, Eiffel, and capital Europe, and all of these context words are like semantically related to Paris, but training to predict all of them, the model learns a rich semantic profile of what Paris is. So continuous bag of word averages context, which works well for syntactic patterns like plurals and tenses, but averaging loss some semantic richness. So like both continuous bag of word and skip gram are significantly better than the older models, despite being architecturally simpler. This validates the more core hypothesis: simplicity plus data wins. So now moving on to next slide, which is like we'll have the discuss the results of a large scale training. So using the like Google belief distributed training infrastructure, you will see in table 6 from the paper all the models trained on the full Google News data sets, which is like 6 billion words, and NNLMs at 100 dimensions, 50.8 total accuracy, and took 14 days on like 180 CPU cores, and that's lot of compute. So like continuous bag of word at 1000 dimension, which is like 63.7% total accuracy, took only 2 days on like 140 cores. And skip grams are like 1000 dimensions, which is like 65.6 total percent accuracy. So it's like, which is like 2.5 days on like 125 cores. So the skip gram at 1000 dimension achieves like 66% on semantic tasks that was state of the art in 2013, and 65.1% in syntactic tasks, which is like 65.6% total. And it does this faster and with the less compute than NNLMs. The note about NNLM at 1000 dimension is telling. It would take too long to complete. The word2vec models are like so much more efficient than you can afford much higher dimensions in the same budget. So the training details is like this belief framework runs 50 to 100 models replicas in a parallel, and each replica processes the data and sends gradient updates to central parameter server, and this uses the ADA grid, adaptive learning rate optimizer, with the minimum batch synchronous asynchronous gradient descent. And this is like kind of a large scale infrastructure that made a Google such a powerhouse in NLP research at this time currently. So now moving to the next slide, the magic vector arithmetic. Okay, so this is probably the most famous result of this paper, the thing that made everyone go like, wait, how is this possible? Like, word vectors support meaningful vector arithmetic. So if you see the formula, analogy of the formula is like d is equal to b minus a plus c. Then we find the word nearest to d. The answer to question of this form is like a is to b as c is to dash. So let me walk through the example. For example, like France minus Paris plus Italy is equal to Rome. The vector France minus Paris captures the concept of capital of the city and add it to an Italy, and you get the capital of Italy like a Rome, which is correct. And France minus Paris plus Japan is equal to Tokyo. So correct. France minus Paris plus Florida is equal to Tallahassee, and which is also correct. So basically, big minus bigger plus cold is equal to colder. The vector big man here, the bigger minus big captures the concept of comparative degree, and add to cold you get a colder. And the model has learned grammar from the raw text. So the, let's suppose next example, like Sarkozy minus France plus Germany is like Merkel. The offset Sarkozy minus France captures the leader of, and add to Germany, and you get the Merkel. The model knows who leads which country. For example, now moving to next example, like Microsoft minus Windows plus Google like is equal to Android, where Microsoft minus Baumol plus Apple is equal to Jobs. So like I want to like you to stop and appreciate what's happening here. The model was never told that Paris is the capital of the France. It was never told that Merkel leads Germany. It's learned all of the purely by predicting which word appear near which other word in the massive corpus of text. And the fact that these relationships encode as a linear offsets in the vector space, that is genuinely unexpected and beautiful. So now moving to next slide, the geometric intuition of this paper. Let me now build some intuition for why the vector space has this structure. Imagine doing PC on the word vectors, reducing them to 2 dimensions for the visualization. You had C clusters like this, like country names France, England, Germany, Italy, and forming the one cluster in the capital cities like Paris, London, Berlin, Rome, forming another cluster which is nearby. And here is the key: the arrow from France to Paris is approximately parallel to the arrow from like Germany to Berlin, which is like approximately parallel to England to London, which is approximately parallel to Italy to Rome. All these arrows are the same offset vector is capital of. Similarly, look at the gender axis, like king, queen, same offset, female version of it, man, woman, and the vector like queen minus king is approximately is equal to the vector woman minus man. This means the word vector space has an interpretable geometric structure. Different direction in the space correspond to different semantic concepts. One axis encodes gender, another decodes royalty versus commoner, and another encodes country versus capital. So, and this structure emerged completely organically from like nothing but predicting some context words. The model has never told what a gender axis is. It discovered it because the distributional patterns in text carry their structural information. So now moving to like some workout examples like end to end. Now let me do a like complete worked example from scratch. Now from a raw sentence, all the way to king, like minus man plus woman is equal to queen result. So now the step one, tiny training corpus. The king ruled the kingdom. The queen ruled the kingdom. The man worked hard. The woman worked hard. Now step two, skip ground training pairs with the window size 1 from the king ruled the kingdom. We had generate pairs like king, the king ruled king, ruled the ruled king kingdom, and so on, and for all the sentence. Notice that king and queen get paired with the similar context words. Both appear near the ruled and kingdom. This is what will pull their vector together. Now step 3, after it is training, suppose we learn these simplified 3D vectors. Like suppose king has like a point 0.9, point 0.3, point 1 and point 0.3, which is like a high royalty and low gender female, and medium action queen like point 0.9, point 0.9, point 0.3, which is like high royalty, high gender female, and medium action man will have like point 0.1, point 0.1 and like point 0.7, which is like a royalty, and low gender female. High action woman can have like point 0.1, point 0.9 and point 0.7, which is like low royalty, high gender female, and high actions. Now step 4 is like compute king minus man plus woman, so which is will be equal to like point 0.9, point 0.9, point 0.3. Now moving to step 5, find the nearest vector to this vector, and that clearly queen, which is exactly like point 0.9, point 0.9, point 0.3, and it works. And the reason it works is that the model learned to encode the same two orthogonal concepts, royalty and gender, as different dimension in the vector space. King minus man removes the male commoner component and keep the royalty component, and adding woman reintroduces the female component, and the result is the female royalty, which is a queen. So now moving to the next slide, which will now we'll have a like a code walkthrough. Let me show you how the actually use the word2vec in Python using a like gensim library, which is this is probably the most common way it get used in practice. First, we import the like word2vec vector from the gensim model, and our corpus is a list of sentences where each sentence is a list of words. And in the practice, you had like millions of sentences, but like conceptually, it works the same. Sentence is like our training data, vector size like 100, and window size is 5, minimum count is like 1, and SG is 1. This means like skip gram. SG is 0 would mean give you like CBO, like the continuous back of word. So after training, we can access the vector for any word. Like model wv king returns a numpy array of like 100 comma, and to find the most similar words to the king, model dot wv dot most similar king, this returns a list of words comma similarity score tuples. So for the next analogy task, uh, king man plus woman, model dot wv dot model similar, and the positive is equal to the king comma woman, and negative will be man, and this computes king plus woman man and finds the nearest word. Ideally this it returns the queen with a high similarity score. So a quick note, with this tiny corpus of a 4 sentence, the result won't be meaningful. So word2 vector need a millions of sentences to work well, but the API and the mechanics are exactly the same whether you are training on 4 sentence or like a 4 billion words, so it doesn't matter. So now moving to the next slide, continuous bag of word versus skip gram comparison. Let me give you like a clean summary of comparing, so you know when to use which. So continuous bag of word predicts center word from context, and skip gram predicts context word from the center word. Training speed, continuous bag of word is faster, about like 3 times faster than skip gram, because it makes one prediction per training step instead of many. For frequent words, both do well. For rare words, skipgram is significantly better. This is because skipgram makes many predictions from each word. So even if a word appears rarely, it still gets many gradient updates. Continuous bag of words, by averaging context, dilutes the signal for a rare words. Semantic task will be like skipgram is better. We saw this in the result, and syntactic task like continuous bag of word is slightly better. So practical rule of thumb, use skipgram when you care about capturing semantic meaning, word analogies, semantic similarity, and downstreaming NLP tasks like the NER or QA, except that it will take a longer to train. Use continuous bag of word when you need speed and are okay with slightly slower semantic quality. For example, when you have a massive corpus and computational resources are limited, or when syntactic patterns matters more than semantic ones. In modern practice, skip grams with a negative sampling, which is like extension, are not fully covered in this paper, so tend to be the default choice for the most applicants. Next slide, sentence completion challenge. Let's look at one more application, the Microsoft Research Center sentence completion challenge. The task is straightforward. You are given a sentence with like one word missing, and a list of 5 candidates words. Pick the word that makes the sentence most coherent. For example, he could not dash the problem alone. Choices: solve, eat, run, sleep, jump, which is correct, will be solve. So now look at the results. A simple 4 gram language model get 39%, LSA similarity get 49%, log bilinear model get 54.8%, RNN LMs, the prior state of the art, gets 55.4%, skip gram alone only 48%, that actually below the prior state of the art. So does this mean skip gram failed here? Not exactly. Look at the last row. Skip gram plus RN and LMs combined will is 58.9% and a new state of the art. The key insight here is the complementarity. Skip gram captures semantic relationship. Knowing that solve and fix are similar, RN and LMs capture syntactic sequential patterns. Knowing that could not is typically followed by a verb. Neither alone is optimal, but combined the cover each other's blind spot. This teaches an important general lesson in NLP, like different model architecture captures different aspect of language, and assembly complementarily models often outperforms any single model. Now moving on to next slide, impact and legacy. The here author releases the code as an open source C++ tool called a word2vec. It can process billions of words per hour on a single machine, and they also release pre-trained vectors for 1.4 million named entities and trained over on 100 billion words. So this paper has been cited over 3000 times and one of the most cited paper in all NLP and machine learning. So what it enables, better machine translation, better sentiment analysis, improved named entity relation recognition, question answering, document classification, and many more. Knowledge based completion and using vector arithmetic to infer missing facts. But the deeper impact is conceptual. This paper demonstrates that you can learn powerful representation of language in a unsupervised way. No labels, no human annotation, just predict context from the text. And it showed that the resulting vector space has a beautiful linear structure and semantic relations encodes the direction. Following a lineage word2vec to glow and fast text from 2014 to 15, which is a better training objective in the subword information, to Elmo, which is in 2018, and contextual word embedding to BERT and GPT, and in 2018 to 19, and deep contextual representation at a massive scale, which is GPT-4, Claude, Gemini, and 23 onwards, and trillion parameter models. Every one of these builds on the core insight word2vec established learn representation of language from the raw text by predicting context. So now we'll next discuss the limitations. Every paper, word2vec has a limitation, and it's important to understand these because they motivated a lot of subsequent research. So first limitation is no word disambiguations. The word bank can means the financial institution or the bank of river. Word2vec gives a bank a single vector, an average of its two meanings, and this is a fundamental limitation of the context independent representation. Limitation 2: no subword information. Playing and played are treated as completely different and unrelated. Even play doesn't share anything with playing, and this hurts the performance of the morphologically rich language like German, Finnish, and Turkish, and where the same root can have dozens of forms. And also, words not seen in the training get no vector at all. And fast text 2016 fixed this by representing words as a bag of characters and grams. So next is the static embeddings, now, which is one strain and every word has exactly one vector regardless of the context. And then I went to the bank to deposit money. Bank means finance, and I sat on the bank of river. Bank means river side. The same vector for both uses. That's wrong. Elmo and Bird fix this contextual embedding. Next is limitation 4, which captures the corpus biases. If the training corpus contains gender biases, the word vectors will encode those biases. A famous example: vector of dog minus vector of man plus vector of woman is equal to nurse. The model learned the stereotypes from the text, not facts about the world. The next limitation is the window based and ignores global statistics. Word2vec only look at the local context windows and it misses the global co-occurrence patterns across the entire corpus. Globe address this with a global matrix factorization approach. Now moving to the last slide to the conclusion. Alright, so let's wrap up and summarize what we have covered. We started with the problem words as an atomic symbol have no notion of similarity. N-gram models and early neural language models were either too naive or too slow. So the solution is word2vec and learn dense vector representation by training a simple model to predict context. The model learns purely from raw text with no human labels. So it has a two architectures, the continuous bag of words which predicts the center word from the context and which is a faster, good for syntax, and skipgram predicts the context from the center word and slower but better at the semantics. The key engineering innovation is like removes the hidden layer and massive speed gains and the hierarchical softmax and reduces the vector operations to log vector and subsampling frequent words. Better rare word representation. So this all are the key engineering innovations. So pointing on the results, it has a remarkable results. These simple operations capture deep structure like king minus man plus woman will be equal to queen, and another what we have discussed. So the bigger lesson from this paper is, I think this is you don't need complexity, you need scale. And if you design a model that can be trained on orders of magnitude more data, the representation it learns will capture structure that more complex model trained on less data and simply cannot discover. And the structure of a human language, it turns out, is encoded in the patterns of the word co-occurrence in text. So you just need enough text and a model that can learn from it efficiently. So word2vec was the spark that ignited the modern NLP. And so thank you. And here next we have the references to this paper. We have used this paper as a presentation.